Good morning, everyone, and welcome to the next lesson on chemical kinetics. So far, in this chapter, we have studied about the rate of a chemical reaction and what are the different factors that affects the rate of a chemical reaction. That is, nature of reactants, surface area of reactants, concentration of reactants, catalysts, and temperature. In today's class, we will study about the activation energy of a reaction and how to calculate the activation energy using Arrhenius equation. Now, we know that for any reaction to take place, the reactant molecules must collide with each other. And for this kind of collision to be effective, the reactant molecules must possess some minimum energy so that they can collide and then they can bring about the formation of products. And this happens with every reaction. This minimum energy that must be possessed by the colliding molecules so as to bring about the reaction is called threshold energy. To understand more about the threshold energy, let us understand this graph. This level indicates the energy of the reactants, which is usually higher than the energy of the products. So ER in this graph represents the energy of the reactants, while EP represents the energy of the products. Now, for this reaction to take place, when the reactant molecules collide against each other, during collision, their energy increases. And for this collision to be effective, they must cross this energy barrier. This highest energy barrier is termed as threshold energy. And this is the minimum amount of energy which the reactant molecules must acquire, must possess to carry out the reaction so that they can undergo collision effectively and can form the products. So once they cross this energy barrier, the energy of the reactant molecules which have now entered into an intermediate state, the reactants which have entered into an intermediate phase, their energy will now start falling until the formation of the product starts. Once the products are formed, the energy becomes minimum. So this peak energy, the energy at this point is termed as threshold energy, which is represented here by ET. So now we understand that threshold energy is the minimum amount of energy which the reactant molecules must possess to bring about an effective collision so that they can form the products. At this point, the reactants undergo or reactants have entered an intermediate phase, which is quite unstable, and so this breaks down into products. Now we come to the concept of activation energy. In order to carry out this reaction, the reactant molecules must absorb the minimum energy that is required to cross this energy barrier and to form the products. So the minimum amount of energy that the colliding reactant molecules must possess so that they can cross this energy barrier is termed as activation energy. So activation energy is in fact the difference between the energies of these 2 points. That is energy, that is the threshold energy, and the energy of the reactants. This energy is usually not available to the reactants at room temperature. So most of the reaction proceeds with the absorption of heat. That means the reaction conditions should be such that the reactants have to be heated so that the reaction can be carried out. But sometimes if the reactant molecules are quite reactive, then their internal energies, which is usually obtained by breaking of bonds, breaking of some old bonds which release energy, can provide the necessary activation energy so as to carry out the reaction and form new bonds to form a stable product. So if the reactants are not quite reactive, then in that case we have to heat the reactant mixture to bring about the reaction. That heat is absorbed by the reactant molecules so that they can cross this energy barrier and can form the product. In most other cases, heating is not at all required. So activation energy is the energy difference between these 2 points, and it is represented by the symbol EA. Activation energy is used to express the temperature dependence of the reaction rate, and the equation with which we can express this dependence is called the Arrhenius equation. We have covered this part in one of the factors we were discussing in while studying the factors affecting the reaction rate, in which we have studied this Arrhenius equation in short. So Arrhenius equation is a mathematical expression that relates the temperature dependence of reaction rate, and it is expressed as small k is equal to capital A into e to the power minus EA by RT, where small k is the rate constant for a reaction, A is frequency factor, and which is related to the frequency of collision of the reactant molecules, means कितना frequently reactant molecules एक दूसरे के साथ collide कर रहे हैं. That is what is expressed in terms of the frequency factor. EA is the activation energy of the reaction, which we have discussed just now. It is the minimum energy that the reactant molecules must absorb so as to bring about the effective collision and to cross the energy barrier to form the products. R is the universal gas constant. T is absolute temperature, that is temperature on Kelvin scale. So this is the Arrhenius equation, which expresses the temperature dependence of reaction rate. And we have studied while discussing the factors affecting the reaction rate that normally the rate of reaction nearly doubles for every 10-degree rise in temperature. And this is expressed in terms of Arrhenius equation. Now we will discuss more about the rate constant of a reaction while we discuss about the order and molecularity of a reaction and the rate law expression. But in general, rate of any reaction is directly proportional to the concentration of the reactants. Or we can say that rate is equal to small k, which is constant of proportionality, into R. This small k refers to the rate constant. And it is constant for a particular reaction. It expresses the rate of any reaction. Now, to find out a modified form of this Arrhenius equation, which can be used to calculate activation energy of any reaction, let us first take log on both sides. Taking log, we have ln k equals to ln A minus EA by RT. Now, suppose that K1 is the rate constant at temperature T1. At temperature T1. Similarly, K2, suppose K2 is the rate constant at temperature T2. Then, suppose this is equation number 1. So, substituting the value of K to be equal to K1 and K2, we can have two more equations like this. So, ln K1 will be equal to ln A minus EA by RT1. Suppose this is equation number 2. Similarly, putting the value of K to be equal to K2, we can have ln K2 is equal to ln A minus EA by RT2. Suppose this is equation number 3. Now all we have to do is to subtract equation number 2 from equation number 3. So doing that we get ln K2 minus ln K1 is equal to ln A minus EA by RT2 minus, this is from equation number 2 ln A, and because it was minus EA by RT2 it will become plus EA by RT1. Now solve this equation, we get ln K2 by K1 because log A minus log B is log A by B. So we get this, then natural log okay, so this will be cancelled, and so we get EA by RT1 minus EA by RT2. Take EA by R common, we get 1 by T1 minus 1 by T2. Further solving this equation, we get EA by R into T2 minus T1 by T1 T2, and this is ln K2 by K1. Now we have to take log base 10. To convert natural log to log base 10, we have to divide this by 2.303. So we have log K2 by K1 is equal to EA by 2.303R into T2 minus T1 divided by T1 T2. So this is the modified form of the Arrhenius equation that can be used to solve or to evaluate the activation energy of any reaction. See, if we know the values of K1 and K2 for two different temperatures T1 and T2, then we can easily calculate the value for EA. Similarly, if the value of activation energy of a reaction is known and at a given temperature the rate constant of the reaction is also known, and we have yet another temperature at which we wish to calculate the rate constant for a particular reaction, then it can be calculated. So knowing T1, T2 and suppose K1 as well as the activation energy, the value of K2 at temperature T2 can also be calculated. So using this modified form of Arrhenius equation, we can do a lot of things like calculation of activation energy and calculation of rate constants at different temperatures. Next, we will learn how to calculate the activation energy of a reaction graphically. For this, let us first recall equation number 1, which was of the type ln K is equal to ln A minus EA by RT. Converting this to log base 10, we have log K is equal to minus EA by 2.303 RT plus log A. Now this equation is clearly of the form y equals to mx plus c, which represents the equation of a straight line. That means if we plot log K on y-axis, here as you can see, if we plot log K on y-axis and 1 by t on x-axis, then nature of the graph will be a straight line. But the slope will be negative and the slope will be equal to minus EA by 2.303 R, which represents M. M is the slope of this line. and C is the intercept, that C is equal to log A here. So the graph starts with here and this point. If the graph starts here, extrapolating the graph, it starts here. This point will be the intercept on y-axis and this will be log A. While slope of the graph m will be equal to minus EA by 2.303 r. Thus we get a straight line if we plot a graph of log k versus 1 by t. Now the slope of the line is used to measure the activation energy of the reaction. So just by knowing the slope of the line, we can calculate the value for activation energy. Because the value for R is constant and the slope is known, the value of EA can be calculated easily. So that is how we can calculate the activation energy of any reaction from Arrhenius equation, and extending the Arrhenius equation graphically, we can also calculate the activation energy of any reaction by measuring the slope of the straight line thus obtained. So these are a few problems for practice. You try to solve these problems. These are based on Arrhenius equation and calculation of activation energy. And you have to submit these 3 problems as assignment tomorrow. In our next class, we will study about the order and molecularity of a reaction. Thank you, everyone.